at various times over the years, from groups bigger than this to smaller than this. So it's a good talk. It's 2 hours. It's full. It's kind of fast. First, everybody has 2627-R3 you're running, right? Why not? 26. Sorry, everybody has their own kernel built, though, right? Okay. No distro kernels? Okay. That's fine. 2626 is fine. 26.2.
That's what we were talking
Which
about.
one? So, for those of you who don't know me, I am the current maintainer for USB in the kernel. I've been maintaining for USB for a long time. I've been a maintainer for a lot of other parts of the kernel over the years, PCI, I2C. I gave those away. Driver core is still maintained. I created new dev, user space stuff. I'm one half of the stable kernel team that maintains the kernel, the stable releases. The other half is Chris Wright, who also lives here in town in Portland. And so I have been doing this for a long time. I'm going to call on some of you guys that I know to help out the people that machines break. So this talk is primarily to get you introduced in the kernel development, make you not scared that you crash your machine, how to load drivers, how to unload them, how things will go for there. Here's the basic agenda: introduction to kernel modules, basics, things like that. SysFS basics. This changes every time because SysFS keeps changing. I'll just point out some new things in there. The basics of USB. USB is weird. It's not like a serial port. It's very strange. I'll talk about the basics of that. How the kernel actually binds a driver to a device. It's a complex thing. It's kind of strange, but in the end, it makes it very easy for drivers to work. How to actually use SysFS, how to make it interact with it from a kernel side and from user side. And then how to actually send and receive USB data, the very last thing. So everybody has a fun thermometer. It works nicely, right? Okay, first thing, everybody plug it in. Watch it break. All right. So you guys better get used to plugging this in. It's going to be a long day. First thing you notice, if you look at LSMod, LSMod is how we see modules. There should be one at the very, very top called LDUSB, maybe. You do have, does everybody see that? If you built your kernel with all the kernel modules possible, you might see that. Everybody see that?
Yep.
Okay, first trick is how we're going to delete that. That's the in-kernel driver that actually supports this device. It supports this device and about 100 other devices. It's a generic device to reading and writing data as far as data acquisition devices. So we need to go find it and remove it. First thing we can do is remove it, rmmod. So that gets us out of memory. So rmmod, and I'll go over some of these commands in a little bit. But now we need to find our kernel. So go to lib, modules. Oh, geez. 27 RC3. Your lib modules directory won't be as bad as mine. Yeah, so if you go to lib modules and then whatever directory you go to that directory name under modules. This is your running kernel. Okay, in that directory you'll see a bunch of fun things. The directory we care about is kernel. Go into kernel, module, drivers, USB, MISC. So you should be in lib, modules, whatever your kernel name is, kernel, drivers, USB, MISC. In there, you will see a bunch of files. One of them should be LDUSB. Delete it. You should not have it anymore. This is the directory that the kernel, the hot plug scripts, actually there are no hot plug scripts anymore. Modprobe actually does it now. Will automatically load the driver based on the device you plug it in. So you want to get rid of that. So everybody get rid of that. Test it out, unplug the device and plug it back in. And make sure it doesn't show up. It should not be there. You guys might have a whole bunch more modules than I do. that work for everybody? That's the trickiest part of it, is descriptive. People that know their stuff.
I wasn't doing it.
Okay. All right, let's get back to this. So let's talk about kernel modules. The kernel is written in C. Very easy. C. Well, not very easy. C is easy. Anyway, hopefully you know C by now if you're in this class. If not, this is not the place to be. Kernel module, very tiny. We have 3 include files. We have a function that we're going to call when the kernel loads the module, and we have a function that the kernel is going to call when we unload the module. To load the module, we'll call it gotemp. These are called gotemp devices. Gotemp init. Init type, and then void. It doesn't take any parameters. In that function, we're going to try and just output a string, because we want to print it to the kernel log and say, hey, we actually got here. In the user space, we do printf. In the kernel, we do printk. You can tell you've been doing kernel development too long when you start writing user space code and write printk. I know some people in this room have. Printk, first parameter for printk is the logging level. What we want to go to the information log, and we say hello from the kernel. And then we return 0. Now 0 is kind of odd if you're used to user space. In the kernel, a 0 means success. Everything happened. It means true, it means good, everything's great. A negative number means it's an error. So when you return it from a function in the kernel, 0 is good, a negative number is error. Very, very, very rarely do we ever return a positive number from a function. We will go to an example when you do that, but that's very minor. You should almost never create a function in the kernel that returns a positive number. So when return true or false, return 0 is good, negative number is bad. That's the way the kernel works. So return 0, say everything's successful, everything's great, and we return an integer type. Exit, we're not going to do anything. Now to tell the kernel that this is a load, that this is an initialization function, this is an exit function, we have some fun macros. For a module to be the load function, initialization function, we have something called module init, called gotemp init. Module exit is the exit one. We unload the module. You guys don't have to type this in. I have had somebody actually type all the code in once. It was amazing. That guy's the vice president of the company too. It's scary. Anyway, and he used Git. Then we have some fun. So it's module init and module exit. That tells the kernel what functions to call. The kernel also has some fun other macros in there. Module author says what your name is. I'll show you how we can find that out later. Module description, you can describe your module, things like that. And the most important one is module license. The kernel, all kernel modules have to say what their license is. Don't lie about it. If you lie about it and say you're GPL and you're not GPL, you just made your course GPL. We had that happen. That was fun. So module license GPL, and that's telling the kernel, this is a GPL module, let it have access to all the symbols that GPL modules can have access to. It's an access control term. Intent, it's showing the intent of the kernel and the intent of the module itself. So anyway, module license GPL, all USB drivers nowadays have to be module license GPL. They just will not work on the kernel module. So that's it. That's the whole module. So, how to build these? Makefiles in the kernel. Makefiles in the kernel are a little bit different. Makefiles are very simple in the kernel. We'll have something, we'll say object M, which is for a module, say hello.o. And then if we're building a module outside the kernel build directory, if we're building a module inside the kernel directory, that's all you need is one line for makefile. Simple, the whole build system automatically handles everything for you. Otherwise, you have to do some fun things, say where our kernel directory is, where our current path is, and then build. So that's it. So everybody, if they go into stage 1, step 1 in the directory. Some people, anybody use Git? Very good. I have a Git tree on this Twitter wall. You can use that. You can switch between the different branches. You can have fun with that. You can use that instead. And that is in the Git tree. So you can see the different stages right there in your Git tree. I'm not going to explain how to do that. If you know how to do it, you know how to do it. So I'll go back. I'll do the. So in there you have a hello. You got to make file, and so you can type make and it should build. And that's it. Does that work for everybody? This is the trick. You just type make. I type M. I have an alias for this CC. Just type make. It should build everything. That's the safe success. Anybody see any warnings? Anything else? If you ever see a warning today, let me know. Because some old kernel versions and newer kernel versions, if you happen to be not running 26, you might have we might have to fix some things. Don't ignore it. The kernel, your code should build without any warnings whatsoever. That's it. So in there, you now have a bunch of files. The original hello.c, you got hello.o that the kernel built a C to an O file. Then we have something hello mod.c and a hello mod.o. The kernel build system builds it. It's a module. There's some fun little tiny things in there. Then the kernel takes a built-in.o, builds it out there, and then finally it'll build a hello.ko. That's a kernel object. It really is just an object file. It's an ELF file. And then it also builds other things: modules, markers, mortar, simbers, things like that, depending on your kernel build system. I'm going to eat now. Thank you. I'll eat later. I'll eat during step 4. Depending, you might not see simbers or markers, and you might have a few other things depending on your kernel build options. Don't know what you build for options, but so hello.ko. That's your file. So if you look at it, it is that's enough. So that's it. So what do we do with these? How to manipulate these modules? Remember, I had the module author, module info, module license. To find that information out, there's a command called mod info. So if you do mod info, hello.ko, you'll see a whole bunch of fun things. See the file name, license, description, simple driver, your authorship. It depends on nothing. We don't really know that yet. Version magic, yours will probably and better look different than mine. Probably. It should have a different architecture type. It might have some big, long mod version things in there. And I can unload my modules and things like that. So that's what the kernel kind of uses to match up modules to the kernel that's actually built against. There's the information. Nice and simple. So you can always run mod info against any kernel module and see what drives in there. It actually depends on nothing, so that's what depends actually is right there.
Why do I have a source version of UL?
You might have different build option turned on. That does MD5 check something against the. I don't have mod versions.
Greg, what was his question? I didn't hear it from here.
Why does he have a source line?
Oh, okay.
Source version.
Source version. So other people might see different things. You might see different processor type, probably. Things like that. That's it. That's your module. That's right there. Okay, so to insert into the kernel, you type insmod. Insmod will insert the module into the kernel. And it inserts this specific one that you're going to tell it. You want it to tell it that one. And if you look in the kernel log file at your D message, you'll see hello from the kernel. So your module loaded, it's there, and it spits something out. I have timestamping turned on. Some of you might not. Your timestamp won't be the same as mine. That's a number of seconds since the kernel booted last. It'll roll over every once in a while. That's good for debugging if you want to see how long things are taking. And so there, you got a module in there. And to see the module, insmod, again, lsmod, like ls, shows the module. Tmessage shows your kernel log. And if you want to remove it, rmmod. So lsmod, rmmod, mod info. And then there's something else called mod probe. Mod probe, if you give it a name, will try and go out and dig through the directory of where your kernel is built against and load everything that is needed to load that module. We're not going to do it with mod probe, but mod probe is a much more powerful tool. We're going to say insmod this specific one. When you're doing kernel development, you want to do insmod, otherwise mod probe is what you want to do. Yeah.
I didn't see anything in the make file that kind of mentioned the .ko or anything like that.
Nope.
Could you just say, how does it know how to make it?
It's smart. The trick is here, we're telling make to run, we're telling it to run in the kernel directory of the source code of the kernel that's currently being loaded against. And we're saying build the modules in this current directory. So change this directory to a different directory where the kernel build system is. In that kernel build system, there's huge makefiles that throw all these rules, figure out how to do the KO, load, all those other files, create all this stuff. And so we're actually running the build out of a different directory. It's then coming back and running out this one. It's a really good document in documentation kbuild in the kernel tree that tells how all this stuff works, how to write your own makefiles, how to do things like that. If you want to build outside the kernel, it's very powerful. You can say, build this specific file, build this specific directory, build this specific subdirectory, build this directory and put the object somewhere else, build it against this other architecture and put the objects over there. If you have read-only with your kernel code and read-only mode and things like that. It's a very, very powerful build system.
And you should appreciate this used to be a lot worse.
Oh, yeah.
It was awful.
Very, very, I mean, come on. To write a real, in the kernel, it's one line. It doesn't get any easier. Well, I guess we had no line. One line of code. And yeah, the kernel build system is awesome. It's maintained by a guy who lives in Denmark. Lives on his own. We knew Meg was crazy. So let's big stuff. Okay. Yeah, and please interrupt me with questions. Echoes. This is an easy class. Okay, so that's it. So you can see it, and then you can RM mod it. First you see it's there. Yes, it's there. Hello. And the fun thing is you see how big it is. It's 1K big, and it's not used by any other module. No other module is using it. That's about it. So there's some fun things. So I have USB core loaded, eHCI and UHCI. You guys might have OHCI. That is your USB controller driver. So actually control the hardware. Talks to USB. You can see lots of fun things there. Don't start unloading modules if you don't know what they are. You can unload your network module even if it's in use. Because how can you ever not? Well, you can make it up. So don't ever log into another machine and then unload the module. I've done it too many times. Don't unload your USB driver if it's controlling your keyboard. Things like that. So yeah, so then you can unload it. And it's done. And we didn't print anything on exit, but we could have. So we didn't print anything that got unloaded. Generally, you want to be quiet when you load or unload your module, because you've seen the boot, all the noise there. It's nice not to advertise your name and your favorite pets and everything else. That's it. So that's step one. That worked for everybody.
It didn't work for me, but it was my fault.
Yeah, okay. Well, I see you now. That's good. That's the first time. Wow. 4 years. Still pitching up. Okay. I'll move on. Let's talk about SysFS. I'm going to not have anything for you to type in for a while. So SysFS. And there's this big, good quote about Linux Weekly News a number of years ago. SysFS looks like a web woven by spider and drugs. That's putting it nicely. SysFS was created because proc was starting to accumulate a lot of junk. And proc had files in there. We added, you've seen all this stuff in proc. There's all sorts of weird things. Proc is for process. That's it. Never, ever add a new file to proc. Yeah, I think you did.
I submitted the patches, but I didn't write them originally.
Yeah. Proc is for processes only, okay? Nothing else. And maybe, not even the memory allocator. That's the but the main problem with proc is it was like big files containing all sorts of fields in the files. If we wanted to add another field or remove another field or do something different on a different architecture, user space tools would break. In the beginning of Linux, top, PS, the whole PS tools would break all the time. They were very, very tightly bound to the kernel. We had to upgrade them all at the same time because of that. You add a new field to some of those and it will break your code. SysFS, the rules in SysFS is one value per file, and that value is an ASCII. No binary, ASCII. One value per file. That's the rule. It's a big tree. I'll show you about the tree in a minute. Proc is for processes, not for drivers, not for devices, not for anything else. If you want to do something debug, you want to put multiple values per files, there's other file systems for you to put it in. Debug stuff, there's a file system called debugfs. You can put whatever you want in there. Anarchy reigns, first come, first served. It's fun. You can put whatever you want there, and it's really easy to use. But that's another topic. So don't put debug stuff in sysfs. Process stuff and prompt. That's it. I can't emphasize it enough. As no patches come from this room that break that. Networking is not an exception. Networking actually put their stuff in sysfs, and then they realized too late that that was actually done, so now they're pulling it out. And they're using that. Bridging, right? Bridging's a bad example of sysfs usage. So, let's look at sysfs. It's in sys. In /sys, mounted by your distro. It's a virtual file system. It's RAM-based. Don't feel bad about adding new files to this thing. It's not a problem. The memory used by this is very, very tiny. Thanks to some people, and some other, Ron and some other people in this, from IBM, we made it so that sysfs works on any machine. We can work on the S390s and 31-bit memory with 20,000 devices. Not a problem. You didn't do that? Actually, don't do that. Some other people did. Manish did it. Oh, okay. Manish is an Indian. Anyway, don't feel bad about adding files. Adding files to sysfs is very easy. The memory in sysfs, if you don't, it isn't used until you actually start traversing through the tree. You traverse through the tree, memory pressure happens, it'll get flushed back out, and you'll have memory pressure back. It is not a memory issue. Don't worry about putting files in sysfs. It's not an issue. Don't, oh, we might have 20 devices. That's nothing. 20,000 disk devices on a 31-bit computer. Come on. We can handle that just fine. So in sys, there are a whole bunch of things. Let's talk about the odd ones first. Dev, sysdev just showed up. That's a fun one. That's because people are lazy. Sysdev is because people didn't know how to map their device names back to, from block and char back to device names. This is not my idea. Anyway, you can see all the char devices in the system, and their sim links back into the sysfs tree. That's your major minor numbers.
Is that legacy? Because
No, this is brand new.
I've seen devices but not dev.
Yeah, okay, you might not have it. You might not enable that as an option in the build. Okay. You might not, actually, that might be in 27.
I don't think 26 has it.
26 has it?
I don't think it does.
Not at all? You sure you didn't just not enable that option? Anyway, okay. Anyway, all right, ignore dev. Everybody has Kernel. Okay, fun stuff in Kernel. Kernel has a directory called debug. That's where debugfs is mounted. Which I don't think I'm. Oh, sorry not. So there's debugfs and /kernel debug. There's all sorts of fun things in there. Scheduler features. Wow, what's that? Wow. Okay, so you can put whatever you want in kernel page table. Oh, what is that?
So you have to mount that, and how do you mount it?
Depends on your distro. If your distro is saying it wouldn't mount it. Right. I work for a distro. I can say that. Actually, this is not random. Slab, syskernel, again, I don't know what's in there. Nothing. There's a whole bunch of stuff in slab, wow. I haven't looked in here in a while. These are kernel-specific things. This is like proc kernel. So kernel tunables in syskernel. Dave, please learn about this.
I haven't done it in weeks.
I know.
Weeks.
So, Greg, does that mean that everything that's kernel tunable related should be there now, and that? And
You can migrate things over, but you
Okay.
but we have the chicken and the egg problem. If you migrate stuff over, you don't want to break old user space rules. So if you're adding something new, always add it there. Don't add it to proc. If you can migrate things over. I've had people put proc CPU info in there. They just never got cleaned up good enough. So it can be done, but just you can't get rid of the old stuff. I mean, Oracle uses proc CPU info. That's a pretty unique number. 1, 2, 3, 4. New event sequence number, the current number of the sequence, new event that's going on. So here's all the new stuff. So we've got kernel tunable in there for it. Module, that's a little more interesting. There's some fun things there. These are all the modules that are built into your kernel or loaded. That's a very good thing. We used to not have this. So you can tell what modules are actually built in. A lot of people build kernels in. And inside there, you can go into, so let's go into USB core. There's some debugging information. That's in the parameters, in the sections. Reference count, how many times it's noted. Notes is, I think, GCC notes section. Holders is who's referencing it. Drivers is fun, that's a new one too. You can see who is actually, what drivers within that module are registered with the system. So there's a USB hub driver, a USB driver, and a USB FS driver in there. So driver names don't always correspond to module names. You can have one module with multiple drivers inside of it. Here's an example. If you ever want to find the driver that's actually in the module, look there. And I'll show you later, in the drivers section, it'll have links back to the modules too. Again, it's a big, nasty web. But here's the fun, parameters. So module parameters are usually at mod probe time. You can change the different specific module parameters. You can do them on the command line, the kernel, or you can change them on the fly. Here's the USB core ones. Auto suspend is if you want to auto suspend your devices or not. No USB is if you want to turn USB off or not. Snoop is fun. You can turn that on and you get a dump out of all the data that goes through the USB subsystem. That's useful for running VMware on top of Linux, trying to debug Windows drivers and seeing what they're doing. We use that a lot. Use both schemes as how things are loaded, or modules are loaded if we use the old Windows way or the new Linux way. Some devices need the old way. Blinking lights shows that Chrome developers have a sense of humor. You write a value, you write a 1 to that. I think it's a Boolean. If you look at these.
Yes, no.
Yes, no. If you write you can write a yes, a Y, yes, a 0, a 1, turn on or off. And you have a USB hub, we'll start blinking the lights back and forth like Knight Rider. There's your Easter egg for the day. So those things like that. So these are module parameters that are in SysFS that can be modified on the fly. Debugging on the fly or not, things like that. That's a good thing. So if you ever want to look at a module parameter, you can look down there. Okay, that's this module. Power is old, but it's still there. That's how you can suspend and resume the device. Just resume state. Here's an exception to one value per file. A state file contains what values can be written to it. It's a kind of exception. Don't put help files, don't cap the file and have it help text be for what you can write to it. I've seen that done. Then people want to translate it. So just document it. In the documentation ABI directory in the kernel, if you ever add a new SysFS file or a proc file, you have to write the new documentation for what that does. We're trying to document all this stuff. Say what it does, how it's used, how to interact with it, and whether it's stable or not. Whether this is something you're just trying out for a while or not. We need to know the relevancy of the API and what user space programs actually use the API. That's also, if we ever change it, we want to know, hey, let's go modify these other programs, make them catch up. That's this power. Bust of firmware. That's where ACPI couldn't figure out where to put themselves. On PowerPC, I think open. What's on PowerPC? That's level. Firmware. Open firmware. That's open firmware. Trees in there. Mem that.
You don't want to know, it's junk. You just put it in the last version.
Oh, hey, all right, I don't know.
It's the EA20 table.
Okay, that's what comes out of the firmware. I said no binary files. There is an exception in SysFS. If you want to have a binary file, I think that might be an example of one where you can dump the raw hardware data. You want to be the kernel be a pass-through. You can get to raw config space from PCI devices, raw config space for USB devices, some sections of firmware from devices. You can just, the kernel's a pass-through only. If you want to be a pass-through only, don't interpret the data at all. It's okay to have a binary file. It's the only exception. It's rare. It does happen. But then again, the kernel's not knowing what that data is. I don't want to see you parse it down to a structure and then dump the structure back out to user space. No, that's not allowed. Raw, just type through. So let's look at the interesting things. FS, there's nothing in FS. You might have Qs over there. Let's talk about things. So in the kernel, we have devices, and we have drivers, and we have classes. I added struct class to the kernel, making it so you can never compile the kernel in C++ compiler. So we have struct class, we have classes in there. And classes are types of devices that interact with the user. We have miscellaneous devices, we have network devices, we have PCI bus, TTY devices, virtual console, SCSI devices, input devices. These are devices that the user side sees. That's a class. It's a class device. Then we have devices. And in the devices tree is all your devices in the whole system. This is a big, giant tree. 1,197 different directories. That's big. That has all your real devices. It shows a hierarchy of all your devices in the system. And inside there, let's follow this. So in the PCI directory, you have all your PCI devices. These are your PCI root devices, the root buses, things like that. Firmware node, that's interesting. If you look in there, there will be symlinks around places. So this is why firmware node actually points back to something else in the Linux system. That's an ACPI device tree. Plug and play member. ACPI, I think that's what. So in there, that's how we see our thing. So I don't know what here's a random PCI device. In that PCI device tree thing, we have a whole bunch of interesting things. We have the class of device, config, device, enable, the IRQ number, device. If you go ls-l, you can see it's actually of type subsystem PCI. It shows it's a PCI device. There is a driver bound to it. And that is the PI, this is my IDE device. So driver goes to bus, PCI drivers, PCI, PIX, IDE. So here's a device. We can see what drivers bound to the device, what subsystem this device is of, what firmware node, that goes back to the ACPI thing. And then if you go into here, we can see links back to the devices. Here's all your devices in the tree. Class devices show up as children of this. So class devices now are part of the big device tree. You can see the virtual TTY devices, you can do things like that. Go back. We make a lot of virtual devices, so they're under sys devices. Virtual, all your miscellaneous devices. Network devices, I don't have anything enabled right now. Your LO, your loopback is there.
So if I don't have a virtual directory in there?
You should. Sys devices, no virtual?
No virtual.
No virtual.
Wow. What kernel are you guys running?
27.
No sys devices virtual.
No.
No? Oh, yeah. Config sysfs deprecated, you guys probably enabled. There's the old mode of where we did not put these things in the device tree, so you enable that. Everybody turn that off. Turn off when you reload your kernel next time. Sysfs deprecated.
I don't want my old code to work, Greg.
Your old code is broken, Dave.
The reason we did this was the rules of sysfs, like I said, one value per file, and things are in a tree. When we first started doing this, some people didn't realize that we were making assumptions on what the tree looked like. So the rules of sysfs is don't ever treat a directory as a directory. It can be a symlink. And we messed up on that. I messed up on that. I made UDEV, and some versions of UDEV was not working properly. We fixed it, changed in the kernel, but in order to get old versions of UDEV to work, which actually was Fedora 3, PowerPC version, we had to enable this thing, because Andrew Morton's box wouldn't boot. He was trying to run a new 2627 or 23 kernel on the Fedora 3 box, which is actually not even supported anymore. So there's that config option. If you turn it off, you get a much cleaner sysfs tree. Turn it off. If you're running a recent distro, meaning in the past 2 years, you should be fine. Even Fedora turns it on. I don't know about Debian.
Both of them? There's deprecated, was deprecated V2.
No, you can only modify one of those because we changed it for a while, so we had to put a fake V2 in there. If you delete it, you only get asked once.
Oh.
That's the thing. In the SysFS tree, there's rules on how you use it. And one of the things, if you want to use a space tool, you document it all in the documentation directory. Don't assume the directory is really a directory. It could be something. Be able to follow that. Just don't do it. So don't do a stab. You need to do an else stab for failure. I messed up on that. Some other people who used to work there messed up on that.
Are you going to blame Dave again?
No, I'm not going to.
Okay.
I'm going to say it's my code. It was my user space.
So if I decided that I'm writing a driver and I think I need a sysdevices RIC directory or symlink, who's going to arbitrate that and say you're mistaken?
I will.
Is it you?
I will come with you with a big stick. So stop. SysDevices RIC is a really odd one because you're not a device. You are a, well, why would there be a SysDevice? There'd be a class, right. I have a sys class RIC cage. Yeah, right. Yeah, RIC, yeah. And platform is weird, and SysDevices. Platform and system are kind of arbitrary. Platform is all the really weird things that don't belong to a bus. They're just on the motherboard. In embedded systems, you see this a lot. They're memory devices. What do we have on my little laptop? I have my PC speaker. I have my serial port. I have my Beza frame buffer and my keyboard controller. Those are platform devices. Those are raw devices. There's a platform subsystem to handle that. Another really weird one is system. So the difference between system and platform is very gray. Systems are things that are in the system but aren't really real, like CPUs. System devices allow you to bind multiple drivers to devices, and we're trying to do that for the whole rest of the tree. SysDevices system will go away soon. That's hopefully soon. CPUs are in there. Fun ones.
Memory's in there.
Memory's in there, Dave. Thank you.
You don't have memory hot plug enabled.
No, it's on my laptop. I want it to work. Is this the one? Here's the fun one. Here's in the CPU frequency directory. Here's the biggest abuser of SysFS. There's a histogram. If you look at how the CPU frequency statistics have been transferring between the different frequencies, here's a histogram of the kernel. That just needs to go away. Everybody agrees it needs to go away. I just need to move it to debug and test. Haven't got around to it. But don't do that. That's a funny one. All right, classes again, devices. Oh, block. You'll notice block is there. And block is there because block came first. Alviro wrote sysblock before we got SysDevice to work. Alviro was one of SysFS's biggest proponents. He helped invent K-objects. He helped invent work on this a lot, and it was the biggest help we had. He made it generic, and it works really well in the kernel, thanks to him. So sysblock, if you look newer kernels, if you have SysFS enabled or disabled, it'll really be symlinks into the big tree. So my HDA device is really devices, PCI, that device, ID 0, that bus number, it's a block device, and it's HDA. My loopback devices are all virtual block devices. That's it. So you guys might have a real device there if you have that option turned on. So that's why block is different. But if you look in class, you will also see block. Sys class block as well. Oh, I got that working. That might be in 27, I'm not sure. So sys class again are types of devices. So these are again in sys class USB, you won't see real devices, you'll just see symlinks back to devices somewhere in the tree, unless you have this enabled. Some places you'll see symlinks, some places you won't. So that's SysFS. So it's symlinks everywhere.
So, Greg,
Yeah.
on class, are we looking at the devices the kernel knows about, or are we looking at classes the kernel knows about, or classes of the devices on our system?
Classes of the devices on your system. Yeah, there won't be show up anything in there that isn't actually bound to something. Except good segue, thank you. Bus. Sys class bus. This last bus actually shows the buses. This will probably go away in about a year, but it's fun to watch right now. PCI, you see a whole bunch of PCI buses. Now here's drivers. So in here you have the drivers that are loaded.
Hey, Frank, what did you say was the waiting here?
Sysbus.
All of them?
Sysbus will probably, yes, will probably get renamed as Sys subsystem, and class and bus will be merged. Because they're really, me and Kai Sievers, who's the guy who took over UDEV from me, thankfully, have been arguing about this for about 3 years now. We're going to go, SUSE Labs has a meeting every year because we all work remotely. We go up to the woods in Prague, so we're probably going to hammer this out in about a couple weeks and get it working. It was working about 2 years ago, but we didn't want to break user space. I think we got everything working now. So Sysbus PCI drivers, like I have an ATA PIX driver loaded, well, no devices associated. There's one that's loaded, but actually isn't in the system. You can think it is loaded. Anyway. So my UHCI controller has a bound to some devices right there. A link from that to what module it is, right over there. Hey, it's not built in, it isn't loaded. Oh, yeah, AHCI is built in. It points to the place in the modules tree where it's loaded. Yeah, you can get lost real easy. Never try and run find. And then play, hey, it's in a cyclical loop. Yeah. Don't follow symlinks. It's supposed to be a cyclical loop. You're supposed to be able to land any place in the middle of that system, in that tree, and find your way around. You can, by doing things, because the kernel emits, whenever you create or remove a device in the system, the kernel spits out a message called a U event that says this device was created and it's at this location in the kernel, in the sysbus tree. Then UDEV picks that up and says, what do I need to do with this? What type is it? Do I need to load a driver? You know, and figure out and go from there. And that's how hot plugging works. So sysbus PCI drivers. I have PCI Express. Those are unique little drivers that actually bind to your PCI Express interconnect, not actually PCI Express, PCI drivers. Okay. That makes sense. Everyone. It's a mess. It's fun. But it works out really well because it's showing a mess because it's showing an internal representation of the mess. This is how the kernel sees these devices. This is how the world interacts with these devices. It isn't simple because it isn't a simple problem. If we want to dumb it down, we won't actually be able to express everything we have. It just comes down. So, any questions? All right. Oh, USB. No worries.
It's if you go in between, yeah.
All right, USB.
Right.
Yeah.
Whatever you explained about the sysfs directories, is that captured somewhere in the documentation directory?
Yes. Sysfs rules.txt. And it is actually the native columns, it's the big terminal. Documentation, sysfs rules.txt. So those are the rules, read that. If you're writing user space programs that use sysfs, read that file. In the ABI directory, you'll see now where we have the documentation for the ABI in sysfs documented. So like sysfs module is documented on what's in there, what's going to be contained, how to use it. And so look in there, it'll explain this kind of thing. It isn't full, we haven't fleshed out documentation ABI that yet, but it's getting there. If the rule is anything you add new needs to get added there, we'll slowly get there. Okay, USB. So, USB's goal many years ago was to replace serial ports and PS2 ports in the back of the system. They want to make something plug and play, they want to make it cheap. They want to make it really, really cheap, put in nice amounts. They didn't necessarily make it one fast, they just want to make it cheap. They wanted me in a phone too. Toshiba was part of it. That never really worked out until now, but that's another long story. So USB devices are weird. You can think of a USB device, there's a big descriptor in a USB device. In this device, it describes everything that's in there. So a physical USB device has one USB device descriptor. That's it. In that descriptor are interfaces. One, two. And these interfaces are how the computer interacts with the device. For really simple devices, like our thermometer, we have one interface. We have one interface. This is a data acquisition device. What they want to do with this is able to have physical devices be able to bind to multiple drivers. And to do that, perfect example is USB speakers. USB speaker is an audio device, and it's also a keyboard. It's a hidden keyboard with little buttons. You don't want to write a new driver for every single USB speaker that comes out that has 4 buttons instead of the last one that has 5 buttons. Another rule USB came out was they wanted to create standard interfaces. You write a limited number of kernel drivers, and they would just work. So every manufacturer wouldn't have to write a driver. So they came up with these common classes: keyboard, audio, storage, USB storage, which really is just a transport for SCSI. USB storage documents about 3 pages thick. It says see the SCSI, which has been no end of problem. That's my notes. Interfaces. So those are interfaces. So these are logical units that your driver will bind to. Your USB driver will bind to these interfaces. Now there is something funny up here at the top of a device that is unique to the device, and it's a config. And that kind of describes what is down here. So there's something weird up here, and every driver can see that, but don't really worry about that. So those are interfaces. Makes sense? Okay. Now it gets trickier. Within those interfaces, we have configuration. So an interface, big 1, 2, big 3. And a device can be in different modes. Perfect example of it, and if any one of these configurations for an interface can only be active at one point in time. A perfect example of this is a device that can accept firmware to it. So it has a normal configuration when it's running. You can switch configuration, it becomes a dumb device, and you can dump firmware to it. Switch it back, you can run configuration. That's a configuration interface. A driver still binds to the whole interface, but the driver needs to be aware of what configuration is active. Most all devices only have one configuration. Make sense?
The config is for the whole device.
Config is for the whole interface.
Oh, there's a config for interface.
Config for interface.
Okay.
Yeah. Oh, that's sorry. This is a device config. This is the interface.
Ah.
And then, within the configuration, there's a setting. And that setting says what type of the configuration is currently running. And those are very, very rarely used, but they're there. You might see them, you might run across them, and you will run across them in a minute where we have these things. So, where's the setting for interface? Or configuration? Anyway, there's multiple ones of these per config. This is how the device is described to the host. So you plug in a device, it reads some descriptors, and we can figure out what everything is.
So to use the example you used before with the speaker, would that be represented by multiple configs or multiple interfaces?
Multiple interfaces, because a driver binds to an interface, not a configuration. A driver for a configuration. Now, the fun thing is, if you switch configurations, the driver can switch. So the firmware download example, I switch configurations on this interface, there's a standard driver for firmware download. The old driver will unbind, we need to bind a new driver to it. It changes the whole way it works. It's a mess.
Can a driver bind to more than one interface?
Of course.
Oh.
A driver can bind. Ideally, you can plug in 100 devices of the same type, and a driver binds to every one of those interfaces. Right? Some devices require that to work as a unique device, one driver needs to be talking to both of these interfaces at the same time. A perfect example of this is the modem driver. For some reason, in their infinite wisdom, they put some control things down here, and the data comes out through the other one. So the same driver has to bind to both of them. So we do some really nasty tricks, because we don't want multiple instances of the modem driver. It's really just one modem device that we have to go poke around in their interface. It's rare. Modem does it, and I think that's about it. USB storage? No. Well, I'm not good with that. So that's that. That makes sense. So this is all just basically a configuration file that comes from the device. You can read it, you get information.
From the same interface, you can have multiple drivers binding to different configurations.
No. One configuration can only be active at one point in time. So an interface has multiple configurations, only one of them can be active at one point in time. So you can't have the firmware download and like the mouse device driver configurations be active at the same time. It's either one or the other. So either the mouse driver or the firmware download driver would be active at the same point in time. Either or. Driver binds to the one interface. So that's how it works at that point. So this device is really dirty and simple, and it just shows up as one interface. Very nice. Simple. To a point. I'll get to that later. So that's,
Can we see those interfaces via SysFS?
yes, you can. You can actually see them through something even older. Go to proc bus. No, Ellie. Proc bus USB. This is not proc. This is USBFS mounted at proc bus USB. This was done in 2.2. Before we had SysFS, before we had any of this. If you look in proc bus input, there's something down there, proc bus PCI. Yes, proc bus. In the devices file, you'll see a whole bunch of stuff.
So I didn't have this mounted by default. I'm not sure.
Right. Distros don't mount this by default for good reason, and I'll go into that later. But you can see this is. You can look in SysFS. All these values are in SysFS, or this file. I like them. You can see that my host controller, my serial number. It has one interface, one configuration. Its attributes are that. Power is none. It is of class hub because it's a hub device. It is bound to the driver called hub, and then there is something called an endpoint.
So what was that file called, and where would that be in SysFS?
It's not okay.
It's not. That file's not.
That file is not in SysFS.
Oh.
I'll get to there in a minute.
Looks like a file.
That would be more than a one value per file. We have all this information parsed out as unique values per file in SysFS, and I will show you that later for your device.
And the only reason it's a mess is because it happened a long time ago.
Actually, this is a pretty readable file. But, yes, it happened in 2 days.
Okay.
We did this in '99.
No, it's not.
So it's been around for a long time. And like said, they said most distros do not mount this anymore, and for good reason. And I'll talk about that later. This describes how to device. So what is in these things? It doesn't tell how you talk to these devices. That's how the device is described.
Hey Greg, I've got about 8 minutes on my video here.
Okay. Want to change?
Whenever there's a natural break.
This is a good way.
Okay. Yeah, I can change now. Thank you. I'm in the back!
Alright, back to USB devices. So, old devices like serial ports, you just start streaming data out and streaming data in. That doesn't really work. When you want to talk to multiple devices, multiple interfaces, multiple configurations attached to the same device. So, USB is a star topology. You have a host, then you have devices. And some of these devices can be a hub, and you have all the devices down there. Your host is your computer. There's a host controller, PCI controller, embedded devices are platform devices. And they're connected to all this. The host goes around, it's a very dumb thing. A device can't talk to a host, host only talks to device. Host goes, do you have any data for me? Yes, no. Okay. Do you have any data for me? Yes, no. Do you have any data for me? Yes, no. Do you have any data for me? Yes, no. And it just goes around and around and around. USB 1.0 speed is defined two speeds, low and high. Low and full. Low is 1.1 megabit, full is 40 megabit. And then high speed came along with USB 2.0, which is 440 megabit bits. This is theoretical maximum. And as you can see, since it's a full structure, it can be pretty slow. How does it ask for these things? So device talks to a host through something we call endpoints. If you read the USB spec, and stay awake, endpoints are complex, magic things that do funny, weird things. It's all, an endpoint is a socket. Think of it as a one-directional socket. Endpoints either go in to the host, or out to the device. That's all they do. One way. It's a socket, a one-way socket. Now there is one other one that does both at home. That's all it does. It's just a one-way socket. So it's a very simple thing. You put data in there, and either it will send you data, or you can send data out to it. And there's different types of these. So endpoints are of different kinds. Oh, and in and out is in relationship to the host. If you're a device and you're writing the code into the device, you got to think of everything backwards. Out actually is going the wrong way. And another word, Linux runs in USB devices now. USB phones, I mean Motorola, all Motorola phones are now Linux. So we had to write drivers for Linux to be devices. So we can't have a device driver. So we came up with the term gadget. So these are USB gadgets. USB gadget driver shows up as a USB device. That's when Linux is running in it. We support lots of those. We do really good. But again, we're still talking about endpoints. Endpoints still work the same way. They're just the order is reversed. There's different kinds of endpoints. There's a control endpoint. And there's one of these per device. It's 8 bytes big, and it is how we get the configuration from the device, and we can do some other basic things. There's one endpoint, it's control. This, the data goes both ways. 8 bytes, very slow. We ask it, we send some data down, we get some data back. That's the control endpoint. That's not good for shoving lots of data across.
What do you think is 8 bytes?
8 bytes big. These are sockets of a certain size. Think of it as a mailbox of a certain size. So in this control endpoint, it can handle 8 bytes of yeah, the size of these sockets are defined. So you can, our mailboxes, it's a one-way thing. So you can write 8 bytes to it, or you can write 8 bytes from it. Maximum. You can write less. If you need to send more than 8 bytes, you have to break it up into 8-byte chunks. Now luckily, the kernel, the host controller driver, in the kernel will break it up for you. You can say send something that's 200 bytes and it'll break it up for you. Except for control, you can only do 8 for control. Control special. So that happens, we ask it and it comes back. Control is right now, immediate, pretty much instant. Then we have something called bulk. Bulk endpoints are either or, in or out, and then they can range from up to 64 bytes, I think, and maybe 128. Bulk is slow. Bulk is, I want to get this data to you, or I want to read this data from the device. And I will wait until it gets there, or wait until it comes back. It is a guaranteed transmission. The host controller figures out where on the star topology, it can schedule the transaction, it schedules them, and it happens. It's not, it's guaranteed it will get there, or it'll tell you about it. It's slow, but it's good. Printers, bulk transaction. Scanners, bulk transaction. USB storage devices, they're bulk, because it's large amounts of data that we want to make sure it guarantees it either comes or goes. Those are bulk endpoints. And we have to schedule them. We have to say, give them, here you go, device, schedule an endpoint, or schedule, send this data down, or receive this data. We have to always ask for it. Just like a bulk, there's something called interrupt. these are either in or out. And they're usually small, 8, maybe 16 bytes big. And these are scheduled. These are periodic transfers. We say a mouse is a perfect example. It has an endpoint 8 bytes big, and we schedule it. We say we're going to get interrupted every X number of milliseconds, and we're going to get 8 bytes at that time. We will always ask the device every so many milliseconds for the data. If it has it, it'll send it to us. If not, it'll tell us no, it doesn't have any. These are scheduled things. These will always happen. We're guaranteed to always get them. So see, if you put a bunch of interrupt transactions on a bus and a bunch of bulk, we have to schedule them and figure out how we can get them there, because these are guaranteed to go through. You can saturate a bus with interrupt, then your bulk will slowly trickle through. It happens. So you have to figure it out. You won't. Most laptops now come with multiple host controllers. So it's pretty much one device per host controller. So you don't have to worry about scheduling that much. That make sense? Control, bulk, and interrupt. Interrupt is scheduled automatically for us. We have to say go. We say go, and then we have to say stop when you want to stop. We'll get notified every time it gets done. That's about it. Make sense? Then there's the weird one. Like interrupt is weird. Like control is weird. It's called asynchronous. And these again are big, 64, 128. And asynchronous data is useful for streaming data, like bulk. They're either in or out. And it's data that can get dropped on the floor. We don't care if it gets dropped. We want to try and stream as much through. If it gets dropped, we get dropped and we keep on going. Good examples of this are webcams, speakers, things like that. If we miss it, if we can't schedule it in there, we want to drop that packet and keep on going with the next one. Otherwise we'll get behind and start lagging. That's what asynchronous is for. A lot of old webcams used bulk instead of asynchronous, and it started to slowly get newer ones use asynchronous, so works a lot better. Asynchronouses are really hard to program. They're tricky. You chain them all together and let them go and try to figure out what dropped and what didn't drop, and fun things like that. Now, as I mentioned before, this is star topology. Things get really, really weird when you start putting fast hubs with slow devices and fast devices associated with it. We have to schedule when a hub can actually, because if we go and ask a really slow device like a USB mouse, which is running at 1.1 megabit, and we're running a high-speed device that's running at 480 megabit attached to the same hub, if we were to say, mouse, do you have any data? And wait for the data to come back, we could have scheduled 10 things at 480 at the same time. So it gets really tricky on the scheduling stuff. Linux and portions of it can't get that right. It's a really hard problem. You don't want to stick an asynchronous high-speed device next to your keyboard on the same device. It just doesn't work very well. If you really have problems, you're really doing media that you care about, stick it on its own root hub, and you're fine. It'll go fast.
So why are you saying star topology instead of tree?
I guess you're right. Star, I'm thinking of the hub and the host in the middle, and it's all talking to everything else. Sorry. But a device can't talk to another device. That's an important point. A device can't talk to another device. You can't have two computers talking to each other through USB, unless you have really two devices there in between that are taking it out. Or if we do a lot of network, there'll be a virtual network device. Can't do that. And the data coming off this thing, there's 4 pins, or actually 5, I think. Ground, plus, or ground, power, and then 2 different things. It's a differential 5 volt that's going. It's a synced 5 volt speed. So you can't put a sniffer on there and watch the data with your oscilloscope. It doesn't work. It's using cross speed. That's how they get going really fast. You can buy some cheap sniffers that'll work, but you need special hardware. It isn't a serial. You can't turn the power on and off the thing. You can't flip a bit on, flip a bit off. It doesn't work. It's also not good for real time. They're not here. The guys in Austin. No, the guys in Austin were trying to do real time USB devices for robotics. Sorry. Or Mike was trying to do that. And yeah, you can't do that.
Why is that a problem?
Because USB latency and fun things like that is not guaranteed. Both will get there eventually. We can't guarantee when it'll happen, right? That's the problem. People try to figure it out and try working on faster processors now. It works better than it used to, especially with the periodic, with the good real-time patches. But USB isn't helping them to do real-time.
Like, are you saying it's just latency is wrong, or that it's not?
It's non-deterministic.
It's non-deterministic. completely non-deterministic.
Is that true with interrupts as well? Because it sounds like you were saying that was guaranteed to happen every X milliseconds.
Interrupt is guaranteed to happen every X milliseconds, and we will get to it as best as we can, but it's a guarantee that's a guaranteed. So we say, give us every 5 milliseconds, it won't be shorter than 5 milliseconds, it could be longer than 5 milliseconds. So, but mice don't care because they are asked for it. They're not even recognizing that there is a periodic timer going on, they're just asked every so often. And actually, the device itself usually says in its descriptor how often it wants to be told to be woken up or asked about that. So it's a non-deterministic request. Don't do it. Yeah.
So is it purely a question of how fast your device will get around to answering when you ask it for data, or
A combination of that is when your device will get around. A combination of the hardware on the host controller where we shove the data down and say, go schedule these things, and it will schedule them when it can. We have no control over that. It's all done in hardware. Especially the high-speed ones, we say, here's a list of packets that we want to have, go to what different devices are we going to read or write, go do it. And we don't want to constantly pull old host controllers, UHCI. If you plug the printer into a UHCI controller, it drains your battery in about 5 minutes. It's constantly pulling, what's going on, what's going on, what's going on. It pushes more and more stuff out to hardware. USB is one of the #1 time or battery suckers off the laptops. And hopefully USB 3.0 will fix that, but it never was designed. So, yeah, don't do real. PCI is bad. So, that makes sense? So, interrupt, bulk, control, asynchronous. We're not going to deal with asynchronous. We're not going to deal with bulk. We're going to deal with interrupt.
With storage devices, those are both in and out kind of.
They are, but there's multiple. You'll have multiple endpoints. You'll have one endpoint that goes one way to send data out, and you'll have another endpoint bulk that sends data away. An endpoint, a bulk endpoint, can only be one direction. So if you look, you'll see multiple endpoints in the device. So that's how that works. You'll see multiple endpoints. So let's see. Let's look at our device. We'll plug your device in. Look at the kernel log. There should be. All right, my device is the sysbus USB devices 2-1. I don't know what it is. Yeah. Yours will be somewhere else. I found this by going, if you plug your device in, you will start seeing some device information saying what hub woke up and what device changed. Look at these numbers. USB 2.1. I have a new low-speed device using UHCI controller and address 5. Descriptors, starts talking about fun things. I just looked at the kernel log running dmessage. So it's not important. We'll figure out a better way to get to this, but I'll just show you this stuff. In this directory for this device, this is the USB device. It has a lot of attributes. A manufacturer is a string. It's Vernier Software and Technology, made this device. Here are all the individual files that were in that Profibus USB devices file. Product, it is a GoTemp version 1.53. I have an old one. You guys might have a newer one. Actually, I didn't think about this. I have one interface in this device. One interface. And this interface actually is going to be this one. So I'm going to go into this directory. And this is what a driver is going to end up binding to. But anyway. Yeah.
What directory are you in right now? I just kind of get you to the right thing.
I think I jumped ahead. All right. Don't worry about that. Next step, we'll be able to find an easy way. Okay. Actually, hey, good segue. How do we find a unique device? In the kernel, we want a driver knows how to bound to a device. As part of device configuration, the USB device has a bunch of attributes, like I said. Configuration, interface. Some of those fields are what the vendor ID is, what the product ID, and what class of device it is. Whether it's a HID class, which is a human interface device, which is keyboard and mice, foot pedals, joysticks, things like that. Whether it's a serial device, et cetera, et cetera. So the kernel driver knows what kind of device it wants to bind to. And there's a macro that we call module device table. And if the driver knows how to bind what device it's going to support, we don't want to have to tell user space what type of device we support. We only want to write it one time. So we do something called module device table. So then step 2, in the directory there, you'll look at the file, go temp. We know vendor ID. The vendor ID for this vendor, they're unique. You have to pay to get a number. This vendor ID is 8F7. Finally, Linux has a number. We got a number finally. I don't remember what it is. We paid our money. They're like, why do you want to be a vendor? Like, well, didn't AIX want to be? I'm like, oh yeah. Virtual devices. We want to do it for virtual devices. Our hubs now show up as virtual devices. And then the product ID. This product ID is controlled by the manufacturer. They have a 16-bit number. They can assign them however they want. This device, this temperature probe is device number 2. The third device they made. I hope they started with 0. And it just works like that. So we create a structure based on this information. It's called a structure of USB device ID. Called ID table, and we use a macro called USB device, vendor ID, product ID. Make a structure. It's an array of structures, and then we terminate it with a null termination of an empty record. That's it. This is all that the driver needs to do to tell the kernel. We now have a macro called module device table. We say it's a USB device and a pointer to our structure. The kernel takes this little macro and does all sorts of magic with it. It exports it to user space. It dumps it out through SysFS. It does it when we load the module. It lets you do all this fun things. We don't have to write INF files to match your driver. We don't have to write the thing in OS X. I don't remember what they're called. For matching things. You only have to write it in one spot. The kernel driver is the authoritative. It knows what it binds to, so we let it handle all the user space stuff. That's the magic binder. It just works. We were very happy when we finally got that working. Early 2.4.0 pre-12 or something. It was scary. Things were changing at the very end. That just works. So we have a structure. So what happens when the kernel sees that device? Plug the device in the USB subsystem and say, hey, I found a device that happens to match this device vendor product ID that this driver just told me about. What do? Well, it'll call a function in the driver called probe. The probe will get a function, will get a structure of an interface. Remember I talked about interfaces for bound to drivers? That's what is bound to the driver. USB interface, you can do what you want with it. And you get a pointer back to the device ID that you passed the kernel in the first place. And you need to do, you can hang some other fun things off of that. That's what you're told. So in this very basic, easy structure, easy driver, step 2, we'll just print out a string to the kernel log that says, hey, I found a device. And we'll use the dev info macro. Dev info was a print K with a special, we pass it a device, an address of a device, a struct device in the kernel. The kernel in C, we do multiple inheritance, object overloading, all this fun stuff. Struct K objects, struct KREF, struct device, struct USB. It's crazy. If you want an example and description of how you do it, there's a book called Beautiful Code by O'Reilly. It's a really good book, written by 30 people. I wrote the chapter in about the USB driver, or about the driver core in the kernel. I think it's free online, but there's a lot of other really good essays by other people. But it describes how that works, how we do object overloading. And the people that really know how to do it right, the G objects and the GTK and the QT guys just scream at us when they see it. But it works. So anyway, dev info, pass it a struct device, and then when the device gets yanked out of the system, we'll say, hey, the device went away. So here's 2 functions. They're static. What do we do with them? One last little step. We need to define a structure called USB device. Oh, sorry, USB driver. Driver, going to call it goTempDriver. Give it a name. Tell what our probe function is. Tell what our disconnect function is. And tell what our ID table is. 4 things. That's all you need to tell it. Using the C99, that's the way you define structures in the kernel. Please do that. And then again, our init and exit function that we had before, we used print K, we will call USB register the driver. And then when we unload the module, we want to deregister the driver. Does that make sense? Nice. Let's do it. unplug your device. Or you can leave it plugged in, it doesn't matter.
Is it more exciting one way or the other?
It's more exciting if you unplug it. It doesn't matter. If you just load the driver, I did load, okay. If you just load the driver without the device plugged in, I have USB debugging enabled. USB kernel will spit out something and say, hey, I registered a new driver called GoTemp. That was that string. I plug my device in. Now the driver's loaded. I get all sorts of fun things. I get the host controller saying a device showed up. The hub found the device. The host controller found the device. We get all the way down here and we say, hey, let's probe. The USB core will pick the first configuration out of one choice. That was nice. The first configuration out of interface 0. We'll create a U event, tell user space we got it. The hit driver, this is the fun thing, will try and bind to the device. Because this device lies and tells the kernel it's keyboard.
Why does it do that?
All right. Under Windows, there's no easy way to write user space USB drivers unless you say you're a hit driver. Windows has a very nice, easy to write interface. So if you do a hit driver, which is a human interface driver, you can write a user space program and control it. You don't have to write a kernel driver. A lot of device companies don't want to write kernel drivers. They just want to ship a program with their device. So they make their device say, hey, I'm a hit device, when it really isn't. Then their program loads and binds to it and goes. In Linux, we got a table about this big of all these devices that say we're really not a hit driver, so don't bind to it. But the descriptors that the device shows up says it is a hit driver, so it tries to bind to it first. So it's got the ID, got the interface, got that, oops, let's let it go. It just says, I don't have the debugging turned on. But then GoTemp gets called. That's the driver we just added. The probe function gets called, we got the ID, and here's our string, GoTemp device now attached. That came from our probe function. And it says the ID of the device, as the driver and the device number. Your number might be different. Yeah.
So there's actually, in that use table you're talking about, this device was listed in there?
This device is listed in there.
So if it wasn't,
we'd have to manually, we can manually bind drivers and devices to drivers from user space. By hand. We'd have to do it by that. We'd have to say, USB hit driver, do that. In old versions of this tutorial 4 years ago, we had to do that.
Why does there need to be a blacklist of all of these devices that lie and say they're a hit device rather than just trying to probe everything else before probing hit devices?
So that would insinuate that we had a hierarchy of how to probe devices in the kernel. And the question was, why don't we do the hit last? It would be nice to have such a hierarchy. We probe in the order that the drivers are registered with the core. We don't have a hierarchy. We've been arguing that we should have a hierarchy since 1999.
Okay.
Nobody's actually stepped up and written it. Windows provides that functionality because he wants to do weird things like overriding the core Windows drivers with your own device driver, things like that. We don't need to because you can modify our core Windows, our core kernel drivers. So it doesn't really matter. We just have it works and go on. The table's huge, and it would be nice to do that in some way. But what happens if, when you plug the device in, the hit driver is loaded? So we go through all the drivers that we have in memory and say, oh, no, we go to the hit driver. Hey, it is brand, it's timed, it's bound. What happens if the driver for this device just doesn't happen to be loaded in time because we haven't seen it before? Right now, we will call up user space saying, hey, this device was found, no driver was bound to it. ModProbe will see that. UDEV will tell ModProbe, hey, a new device was found. What driver do we load? It'll figure it out by that module device table, load the right driver, then it'll get bound afterwards. So even if we had a hierarchy, we would have to know that the user space binding had failed. How are we going to do that? You want to stall in the kernel, wait for user space? So that's where the hierarchy argument dies. Everybody goes, yeah, you're right. So we've survived without it. The hit table of blacklist devices is writable from user space. So distros and YAS, I know you can add more blacklisted devices that don't have an updated kernel. So you can modify them on the fly. There's a number. I'm 2-1, so this means I am, there's a hierarchy here. I am on hub 2, first device, first interface, 0 config? Interface, 0 interface, first config. What did I got config? Yeah, you're right, that's what config. Anyway. Or it's port. This might be port. 0th port on that first hub. It's documented. It's unique per device. And we try and make it unique per boot. So you boot and you plug devices in the same spots. It should kind of get the same thing, but you will get a different device number. So our goal is you want to be able to figure out the topology. You don't want to figure out a random number that was assigned. It kind of works.
I'm not seeing that information in my new message. Do you have extra?
I have USB debugging turned on. You should probably just see this GoTemp USB device method. Right? That's the important one. That's the one you added. You might see this bound thing here. New USB device bound. Is that coming 2627? Anyway, there's fun things. So, how do you tell unique devices apart? And there's things in there. You can have a serial number. Serial number. This company's serial numbers. Nobody should have the same serial number I do. The fun thing is that serial number is not guaranteed to be unique. So mice, all the same serial number, which is a pain in the ass. Well, think about it. You want to control 1 mouse per terminal, and if you have 6 mice plugged in, how do you find which mouse goes this and that? Printers used to not be unique, and finally they mandated printers have to have a unique serial number because you start up and you say this printer was my color and this was my LaserJet, and then they start up in the wrong order and you print the wrong thing, the wrong one. Serial numbers are actually unique for printers. But this is so they can be cheap. I mean, you can make a mouse today with USB for under 5 cents. When it first came out in '99, it was about 50 cents. This stuff is dirt cheap. It's a really dumb device. The controller in there is a 1.5 register controller. I used to do USB controller firmware. That's why I came to Linux. I wrote firmware for this device. Anyway, so remember this number, 2-1.1. So let's find it. It's sysabs. Let's go to /sys/USB. And we're going to cheat. We're going to go to drivers. In drivers, we have GoTemp. That's our driver. We know it's bound to something. There is some files in there. That is the device that's bound to my driver, and there it is in the tree. There's the modules assigned to. Here's a new ID. We can dynamically, on the fly, add new IDs, that device ID table, to the driver without recompiling the kernel. Again, distros do this for PCIDs. Intel is infamous for coming out with new hardware and incrementing the device ID. And that's all they do. So we have to build new kernels for every Intel hardware comes out. It's horrible, all right? It's horrible. We've been yelling at them for years and years and years. They don't do it. So distros is always a mad race to get the device IDs in before they come out. IBM, thankfully, on their few devices they have, don't do that. Unbind, we can bind and unbind a device from a driver manually. If you want to do that, you can say device unbind, bind. That's one thing. And uEvent. uEvent is the event. It's writable only. Oh. In the kernel, it's because of the device. Oh, it's a driver. Anyway, if I want to write to if I write to uEvent, the kernel then emits the same message that it sent to user space. That's how, at cold boot time, a whole bunch of devices in town, we first init, we walk the sysabs tree, tell the kernel, hey, send your messages again, and it looks like everything is plugged in. Nice hack. Let's go into the device that we had, but back a directory. So go into your directory, back one. So highlight the whole thing and go back. Just if you want to go to the root, 2-1. So this is the USB device, the whole big thing, not the interface. And here, you see the driver will be bound to USB, because it's USB, you have to have a driver. We have one endpoint for the control, called endpoint 0. ID product, vendor, manufacturer. If you cap that, that'll be veneer. Serial number, quirks, products. I think we can cap uEvent here. Here we go. cat view event. This is some information that was sent to the user space when this device was added. Major, minor, device type, the driver is bound to it. Device where and proc bus. Oh, that's for USB events.
We're not a single value again, right?
This is not a single value. Because this is a representation of what was sent to user space. What was sent to user space was not a single value. There was a chunk. It was a netlink message. Boom. So, yeah, it's a single unit. Yeah. I won't argue that one. Well, that's a kind of the tough thing. If you look into block devices, we have statistics for block devices. Block devices, we had every unique file per type of statistic. You wouldn't be able to accurately gather a snapshot in time. So we have to look at the statistics, and it spits out anything at once. Again, it breaks down in time. We're flexible. I don't like to say we're flexible. I know you'll argue that. So this is a device. So in here we have the interface, and this is what our driver really bound to. So going to the device itself, here we'll have a driver symlink that goes back to our GoTemp. We'll have an endpoint. So this is saying we have one interrupt endpoint. It's the 8 is a direction and the 1 is the number. I guess it's, I'm going to have to look it up again. The mod alias for this device, you can't mod alias. Here is the mod alias for this device. We're vendor ID something, we're product ID something, or the device descriptor, blah, 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 blah. Mod probe, you can type mod probe this, and it'll automatically load the GoTemp driver.
Wow.
Tricky.
I think GoTemp is easy to remember.
Exactly, but the kernel doesn't know that. And here, if you look at mod info on your GoTemp driver, there's an alias. It says USB, we're going to handle USB, a vendor ID of that, a product ID, descriptor 0, the descriptor class of anything, descriptor subclass of anything, product subclass of that. And so that is mod alias, mod probe, knows the aliases. If you type the big long module, it'll handle and work on it. There's the magic of that. So that's the device. The number of endpoints, alternate setting, class number. Everybody see that? We're bound to the device. You yank the device out, you'll become unbound. You yank the device out. No, look, we're in the same directory. Yeah, that goes away. Bus, USB, GoTemp, driver 7. You have no driver, no device in the driver of GoTemp that's not there. If you look in your D message, we will see GoTemp, USB GoTemp now that's disconnected. A U event got happened, the kernel told user space that the interface went away, and then the USB device went away. And then we suspended it. That's a bit falsely. Did some debouncing when things really went away. So it's binding a driver to a device.
How does the driver bind to multiple interfaces on the device?
A driver says, I am okay with binding to this device, or this subclass. So we know that we're going to handle any interface that happens to show up with vendor IDs, veneer, product IDs. Will be bound to the device. Because we know this device only has one interface on it. If you're a class device, like a keyboard, we bind on the class. The classes are associated with the interface itself. They got complex there. So very rarely do you have a vendor-specific driver, like this one, bound to an interface and have something else bound to another interface. Because they're rare. Hopefully we don't have many vendor-specific drivers. Unfortunately, that's true. We have lots of vendor-specific drivers. Everybody wants to do something different. Everybody's unique, like everybody else.
So when we say LS mod, we're getting a list of modules that are loaded. But if we have multiple, say, GoTemps installed, we're going to be creating multiple instances of our device structure with all of the customs hanging off it things. How is that represented? Or am I missing something?
How do we do that? You have one driver, and you want to bind multiple devices for one driver. This driver is going to handle multiple ones. Let's do that. It's like, I'll pay you later. So let's create a structure. We're going to hang this structure off our USB interface. We're going to call a goTemp. We're going to keep a pointer to the USB device, because we'll want to do something with it later. And we'll have an integer of the temperature. I need to change that. Spell that. Not a temperature. The temperature value. We want to figure out the temperature of this device. So that's an integer. So let's make a structure, okay? So whenever we find the device in the probe function, we are going to create a structure on the heap of structure type of goTemp, struct goTemp. So to start off with, we're going to cast backwards from the interface to the USB device by doing some magic function there. We're going to make a structure called gdev, which is our goTemp device. We're going to kzalloc, which is allocating 0 build off the heap, strives of struct goTemp, and the type. Whenever you allocate memory in the kernel, you can tell what type of memory or what state you're currently in at the moment in time. GFP kernel is almost what you almost always use. That means, kernel, give me this memory. You can go to sleep. You can put me out to the pasture. You can swap me out. You can do anything you want. I need to get this memory eventually. If you're in interrupt context, you can just say GFP IRQ or atomic. Saying I'm in atomic interrupt context gives me as fast as possible because I can't, and you can't put me to sleep to do that. This way we can page out, we can swap things out and get it back. Since we're in probe, our probe functions always run in a task context. We're not sleeping, or we can sleep, we can do anything we want. We don't have to be fast here. You plug the device in. We're not talking about microseconds worth of accuracy of speed. We can do whatever we want. We can go to sleep. We can do whatever we want, and we'll get there. It's okay. We can call it user space and say things showed up. We can do things like that. We don't worry about speed. The kzalloc, we allocate a buffer filled with zeros, and we always check to see if we actually got it back. If we didn't get it back, it would be null. We need to do some error. We can error out. Return a negative error number. There, we failed. Probe will fail. It'll tell the user, tell the other thing that it failed, and it'll die out. That's the way we do it. Then we want, since we have a device that can go away at any point in time, this device is our reference counter. We want to save a pointer to our USB device. We need to save a reference count to this device. At the very bottom down here, we need to grab a reference. The kernel uses get and put. It's kind of backwards from some other C++ idioms. We want to get the device, we pass it to the USB device, and we're going to save off the pointer. That means now we know our pointer is good. Our pointer will not go away. The structure, if you hang up the device in the system, it will not be cleaned up. It will be cleaned up when we're done with it. We'll say put, and it can be cleaned up at that point in time. As long as we're ever using it, we need to grab the reference. This is very important in the kernel. This happened in the 2.4 days, 2.3, 2.4. We made the kernel dynamic. We can add and remove any type of device in the kernel. 2.5 really took that to another step. Everything's reference counted. Everything's dynamic. There are objects that are floating around there with who knows what attached to it. When the last reference goes away, they die. We have structures. If you need to do that for yourself, there's a kref structure, a k-object structure that'll do this stuff for you. Don't write your own reference counting structure. It's already done for you. Then we want to save off this pointer to this gdev structure. And we set, you can call it USB set interface data. The interface data has a place you can store it. Pass the interface, pass it in. And then we say, hey, we got it. That look good? So we're basically creating a structure, attaching it to it, grabbing a reference, and attaching it to it. And likewise, when we disconnect, we want to free the memory when it goes away. So we get the interface data back. This is a void pointer. You don't have to cast void pointers. Don't cast it. We set the interface back to the device back to null. We put the device, we free the structure, and then we say we're disconnected. Put the device is the last thing. Don't be referencing that gdev. After we've done that, it could be gone. Makes sense? I think this is all step 3 minutes. Yeah. You can run it. It won't show you anything else unless you happen to be out of memory, and I really doubt you will. If you do, something bad. Okay. So that's pretty boring. How do we do something? When we went down into the bowels of that systemS directory for that device, we want to create a systemS file. We want to show the temperature of this device in the systemS file. We want to cat it, want to read it, And, well, we don't want to write it. We can't change temperature. So how do we do that? Sysevents, to create a file in Sysevents is very, very simple. I had a big, long argument with Dave years ago that it was hard to do. We're down to 3 lines of code now. Thanks. Proc files is like 20 lines of code. We're down to 3. So we have, for Sysevents files, we have a show function and a store function. Show gets called when a user casts the file, wants to read out of it. Stores when you want to write into the function, or write into the file. For our file, we're not going to go right into it, so we only need one function. We only need a show function. So we're going to call it show temp. The function, this is a specific structure, our signature that all Sysevents, all devices in the kernel have. They get past the system struct device, a device attribute, and a buffer. The buffer is where we're going to put the data. Return a size t, and then we're going to figure out some things. So we get past the device, so we need to figure out from that device that we really are a USB interface. So we just know this. And we know this because we were being called. We were called, the kernel knows it signed the right thing. Here's where all the really object-oriented people start screaming, running around. We're just knowing this. We're just casting back raw C pointers through arithmetic. We're not doing type identification. We're not doing anything like that. You just better know what you're doing. It works. It's fast. It's lean. And it forces you to actually pay attention to what's going on. You can't get away with saying, oh, I'll have a show function for everything, and I'll cast based on the type and whatnot, and you can get complex and messy. Lena said this is the way it's going to be. People argue about this for years. They still argue about it. I think it works out pretty good. It's tricky, but it's fast, and it's lean. So anyway, so we get an interface, and then we get that interface data off there, pointing to there. And all we're going to do is print into the buffer the temperature. Now, what did I do wrong? Where's the security?
How big is the buffer?
How big is the buffer? Yes. I'm guessing that the buffer is going to be big enough to hold my integer, right? And I'm right. If you start caring about how big the buffer is in your show function, you are not putting one ASCII value in. You're printing a table. You're printing a whole bunch of junk. It's going to be page size by virtue of the way the kernel works, but we don't test for that. Because I'm printing an ASCII, an integer can't be bigger than page size by printing out an ASCII. You just do that. If you start doing, if I see SNPrintf and you're testing for it, I know something's wrong. Don't do it. That means you're trying to think of, oh, it's not going to be. You only need to have one integer. Or a tiny little string, okay? Not going to do that. Yeah. That's it. And then we have a macro. We say it's a device attribute. We call it temp, temperature. It's going to be a mode, read of user, group, and owner. And the show temp is my show, and there's no store function, null. And that's it. That's all you do. And in the probe function, we're going to register it. We're going to say device create file, point to the device, and we're going to say device attr temp. This created a structure called device attr temp based on the name. And then we disconnect it. We're going to remove the file. Always remove the files you added to the kernel. The kernel will try and clean up after you. If you don't, and the device goes away, we usually get it right. Sometimes we don't. Try and be good. If you create a file, remove it. And you have to check the return value of device create file. The kernel, the build, will complain if you don't check it. It could be wrong. It could be trying to do multiple devices, multiple things. Check it. Handle the error properly. So we're down to tiny structure, macro, 2 function calls. Can't get any easier, Dave. Way easier than proc, right? I finally converted you in Mark. It was a long argument for many years.
So even if you fail there, the disconnect function will be called, and that's where you remove that reference to your memory block? Or?
And if device create file fails, yes, if my probe function, no. If my probe function fails, my disconnect will never get called because my probe failed.
I don't see a call to put.
Oh, I'm talking about
put device. Put that.
I added that. The kernel forced me to add that last night. I wasn't checking for that on the older version. So yeah, send me the patch. In the very final version, it does it right. This driver's been in the MM tree for about 5 years. It works. So that's it. That's how you make a template. So Let's make it. So go.
Rick, you were saying very thoughtful for that time.
Yes. Well, you're ahead of me. So if you plug your device back in, you load your new driver, and you go to sys/USB drivers, go to whatever your thing is. You see a new file called temp. You can cat temp. And right now we're just putting back, we just have to pick anything, we'll pick 42. It's not real value, but we're showing how to add or move some stuff. So does everybody see the temperature file in their device after they loaded stuff? Everybody?
Not seeing it.
Did you unload the old driver?
Yeah.
Did you load the new one?
Yeah.
Did you point down into the directory that you were in?
No. Continue. Oh.
That's
Dig in here.
Alright.
Where is it? So go into sys/USB drivers, go temp, whatever the directory for your device was assigned, and then and that is because we initialized it in the code to be 42. Now, something interesting here. When you call device create file with this data, you need to be ready at that moment in time for that file to be called. That's the show function to be called. You can't set some more things up below that. You can't do some other things. It could be called instantly before this function even returns. So the interface data better be set up. You better have everything initialized properly. Any pre-initialized data, it needs to be called. The same thing happens for your probe function, or when you register the driver. When I call register, USB register, this function will not return if I have devices plugged in until the probe function is called. So if you need to set something up on a driver level, you better initialize it before you call USB register. It could be called. Whenever you call something passing in a function pointer to the kernel, it could be called before your function returns. So make sure you have everything set up. We've fixed so many bugs like that. So many races. Okay, everybody got it? All right, we're almost there. So how do we actually send data out to USB? This data is a vendor-specific data. It's not hidden. We're faking it. It's an endpoint that's 8 bytes big, and it sends out in a packet format. The manufacturer told me that there's a whole bunch of different commands, and then the final version of the driver that's there. One says start initialize the device. We send it a 1A command, and start sending measurements back. We send it 18 times. And then here's the structure. We'll send it a command and parameters. Command is that, and the parameters, wherever the parameters are for that specific thing. It's a structure, 8 bytes big. We use U8. U8 is all 8 bytes big. Don't use char, uint char t. That's not. That's user space. And we pack it to make sure there's no padding. So to send the command out, we will create a structure of packet. A return value, we allocate the packet. Now, USB is tricky in that you cannot send data on the stack. Some host controllers, some architectures will not. You cannot do that. We need DMA-able memory. The ARM platform is known for not being allowed to do that. So if you want to send 1 byte out USB, you got to declare it now. It's a pain, but you got to do it. So we create a structure, output packet. We make sure it's there. We set the command to the packet based on what was sent into us. This is just a structure to send out a command, and then we send it.
So the stack isn't DMA-able on ARM?
Nope. No.
Is all kernel memory, or do they have to use personal allocations?
They have to use KL. KMalloc will give you DMA-able memory.
But it doesn't get below 16. I mean, not on the old DMAs, right? It doesn't give you under 16 bay.
The old DMA is really ISO. That's not DMA-able as we're talking about. That's ISO memory. Everybody knows 16 bits, right? Yes. So let's send this packet out. Since it's a control message we want to send out to the device, we're going to send out a function called USB. control message. Hey, we pass it in the USB device we're going to send it to. We say, this is the endpoint. It's going to be a send control pipe. Based on this endpoint, it's going to be address 0. We just know this. We know this device only has one. And then there's the structure. These are defined by USB structure. That's why they're in Hungarian notation. The USB spec specifies it. There's a request type. There's a request type, data, and then some other data. We send the packet. Now here's the fun thing. These guys, when you send the data down to the device, data across the wire on USB is in little endian format. So I send out 16 bytes here, bits. It's going to go out across the wire in little endian format. These guys have this device working on the Macintosh at the same time. So they got it wrong, so they made their device accept both big and little endian format. So they can handle 00002 or 0200. They work around the driver bug in hardware. You can tell they're a hardware company. These guys are really cool. They're Veneer Technologies. They're right around the corner in the old Nike building. They've been around for a long time. They make devices for high school laboratories and early college laboratories. They're run by electrical engineers, teachers. They make, I think, 200 different sensor devices. They now have a handheld device like this that you can plug things in. That handheld device runs Linux. They're really nice. They're really good about this stuff. So if you ever need any sensors to do something that isn't like college laboratory grade, real specific stuff, they sell cheap devices for choices. Anyway, you send out a control message. You check the return value. Here is a point, here's a message, so the data will be sent out the USB bus, and we'll wait for it and it'll come back. We'll sleep, come back, and see if it succeeded or not. The return value tells whether we succeeded or not. This function will return a negative error number if we return an error, 0, or return the number of bytes that were actually transferred. So we need to check to see the return value is the same size as the structure that we passed. If it is, then our real return value will be 0. We're free. Otherwise, it's a negative number, and we'll return the negative number. Here's an exception to that we will return a positive number, usually on writes or reads. There we go. So we send out a control message, wait for it to come back. Sound good? Yeah.
So USB control message will just sit there and sleep until the result comes back.
Correct.
Is there an alternative for if you don't want to sleep?
Nice segue. Yes, I'll tell you about in 5 minutes.
Okay.
Yes, there is. This is the way USB 2.2 or Kernel 2.2 works. We could only send out messages one at a time. It worked. It was slow, but it worked. We only had nice devices. We didn't even have any storage. We had floppy. I think we finally got this floppy device working. There was no USB storage devices yet. Anyway, let's see how it functions. When we initialize this device, we will send out a command of initialize, and then we'll send out a command saying start measurements. Great.
What about that hex 21?
That hex 21.
Yeah, in the
under request type?
Control, yeah.
These are defined by the USB spec. It's a big table that says I'm going to send a type of set report of a request type with that, and those bits mean something. I don't remember what they are. You can look them up. The manufacturer said send the message type of this, and I'll respond.
Oh, okay.
You can either sniff the packets from the Windows driver and see what they're doing, or if the manufacturer's nice, they'll tell you what to do. It's not. It's just arbitrary. It's what the device is sniff.
So this send command, do you typically have to write that function? Sorry, the send command function. Do you typically have to write that for each driver? Because it seems very generic except for that one value.
Well, not all devices send packets that are command parameter size. They might send a command that's 20 bits long or something like that.
Okay.
So it's very vendor-specific, device specific.
It's a packet.
It's a
Yeah.
packet. So let's do real data. Like you said, this is slow, so we need to figure out how to go fast. So we stole something from Windows called struct erb. It's USB request block, and they're dynamically created. We can fire and forget. They're just like SK buffs in SK buffs in the networking stack. They're high data rates. We can throw as many as we want as a host controller. Say queue all these up, and we'll be notified when they're done. If they fail, they don't fail enough. So we can keep the hardware happy. With that USB control message, we send a message down. It came back up. By the time it comes back, we process it, and then now, the bus has gone around a couple more times. There's some empty time on the bus. We saturate the bus. We say, here's some big packets to go handle. It's much faster. USB storage, all these big devices where we care about speed, we start using struct erb. For little tiny things like control messages, this thing we don't care too much about. Except we want to be notified when this is device has some data. So let's do that. So let's change our structure for our device. Instruct gotemp. We have our device, we have our temperature. We will have an integer, an interrupt buffer that comes in. This device has one interrupt endpoint. It's in direction, meaning to the device. Oh, sorry, to the host from the device. We have a buffer for it, and we have an herb. We need to create an herb for this. Herbs don't have buffers assigned to them. We have to assign them manually. There's our buffers. Let's create it. But where do we send this herb to? So we need to find the endpoint that we send to. And we know the interface, the current alternate setting of the interface, and we know endpoint 0, and we're going to set description is going to be the endpoint structure. That's a structure. So that we just know that because it's one device. If you look in the final version, I can iterate over all the endpoints and find out what direction is pointing which way, and we can find the right one. We're going to cheat right here. Then we need to create a buffer, and the device tells us how big this endpoint buffer is. It's a WMAX packet size. That's a 16-bit value in little endian format because this came from the device itself. So we need to convert from little endian to CPU style format. That's very important. All these structures that come from the device or to the device raw are in native format. They're in little endian format. We need to convert buffer size. We allocate a buffer. We store the pointer. So now we have a buffer. So now we have a buffer that's going to go to this. Now we know how big it is, and we know the endpoint it's going to go to. Good?
I've got 4 minutes again. I can't believe it's been another hour.
Well, all right. I'll go fast. I'm almost finished with them. Okay, integer herb. So we will allocate an herb now. Call USB allocate herb. 0, the first parameter is number of isocronous packets. We don't have any isocronous packets. Again, we're doing it in kernel. We can sleep. We save a pointer to it. That's it. And then we fill it. There's functions to fill it. We say we want to fill our herb. This is USB device. This is the endpoint. This is the USB device of the endpoint to the endpoint address. Here's our buffer. Here's the size of the buffer. Here's our callback for when this herb is finished. Here's the structure that we want passed to our callback. And here's how fast we want this interrupt herb to go. You can change.
Thank you.
We say submit herb. Hey, I did not. We say which herb we're sending off, and we send again if we can sleep or not. And then we check the return value. And remember this, that callback could be called before this function gets called returns from. So you need to have everything set up. So this herb will just start going and going and going. And when it goes, when it fires, it'll spit some data back. Now we know, because the manufacturer told me, that here's the data that comes back. How big is it? It's going to be 8 bytes big. And here's the structure. It's going to come back. The number of measurements in this packet, a rolling counter, so you can see if you missed any measurements. Measurement number 0, measurement number 1, measurement number 2. This is their structure for all their different types of devices. For this little thermometer, we only care about the first measurement. Now it's in little endian format. We say it's in little endian format because the compiler, if you try and assign this to like a native 16 integer or whatnot, the kernel compiler will say, hey, stop, you messed up. We do these checks at build time instead of runtime. It works out really nice. There's a structure that's going to come back to us on this interrupt endpoint. Good? Here's our callback. We're going to call it read interrupt callback. We pass an herb, and we don't get past that anymore. Right? Just herb. That's all. That was a good example of one architecture in the Linux kernel affecting so many different parts. The Spark architecture, this herb callbacks come at interrupt time. You're in interrupt context when these come. The Spark processor wanted to pass its keyboard state to the debugger at interrupt time, so every interrupt callback through USB had to handle the structure of the CPU registry for one tiny driver. Luckily, we fixed that. It's not there. Anyway, we'll do that for little odd things. Don't say we're not talking. So, you pass an herb. In the herb is a context structure. We passed it back, and we know it's going to be our gotemp device. Our transfer buffer is our measurements. We just cast it to our measurement structure. Our status we get out of the herb. Looks good. We switch on the status. We know what would happen if it was a 0. Everything was good. These different errors happen. We know it's being terminated. Shut down. We need to clean up. If a default happened, if it isn't one of those, we don't know what happened, and we will error out. Good. And then finally, we'll actually read the data. So we'll read the data at a measurement 0, structure. We'll pass the little endian value, little endian to 16 to CPU, which is our native type, whatever happens to be, stored in the structure temp. And then we will resubmit the herb. Because there was an interrupt, we know we need to submit it again. We do it. Atomic, now that we are in interrupt context. Here we just save out the value into another structure. We don't want to do any complex processing, we don't want to do anything else. We are in interrupt context, so as fast as possible. We submit the herb, and then we get out of there. If the herb didn't submit properly, we say, there. That's our callback. And there we modified our herb, our value in our structure, so if you do a system best read, it'll read that value. Makes sense?
What allocations is it doing internally?
This?
Yeah.
Some host controllers, in order to link up herbs onto its internal device structures, need to allocate memory for those structures. Comes in. We want to get rid of that. We want to pre-allocate the structures at USB herb allocate time. We haven't quite got there. It's arbitrary whether it really matters. We are running USB as fast as the hardware will go. We run USB 2.0 from user space drivers, which passed in 2 days, as fast as the hardware can go. It's been the fastest one since the hardware came out. We've blown away Windows for years. They finally almost got to us with this. This actually slowed down some Windows drivers. So we can go line speed. We can do lots of things. 480 megabit is really slow as far as CPUs go today. We can do lots of stupid things in there. When USB 3.0 comes out, I don't know how fast it's going to be. We might have to pay attention to a few of these things. Do pre-allocations. Start being more like a network. We're going to have to start pumping more data out. So right now we can dynamically create things in interrupt context.
Is all of this preamp safe?
It's all preamp safe. I hope so. You're running it. Why wouldn't it be? You're in interrupt context. We're sleeping in atomic. We're calling everything right. We're grabbing spin locks only. No mutexes or semaphores. We've been this way since 2.2, so we should be okay.
So in this case, it seems like we're making the assumption that we can only have one herb in flight at any given time because we don't submit a new one until we get one back?
Not at all. You can submit 20. But for this device, yes, we're only caring about one at a time.
This device, yes.
This device, I could create an array of 20 of them, send them off, and done. So fun things you can do, and I did this for a while until we figured out the problem. Some of these USB serial devices are a Palm Pilot. You want to shove data to those things as fast as possible. So if data comes from user space, we say, hey, let's create an herb as big as possible, or chop up into a bunch of them and throw them at the device. And then when the interrupt call gets done, we just don't touch it. And the herb will get automatically freed up on its own. It gets freed up to do the reference counting, we can drop the reference, and things like that. And it'll just happen. We can pump it, and it'll go as fast as line speed. Until somebody realizes you can half dev null the dev pilot. Take that in the box. Because you're pumping data as fast as you possibly can through the device. So now we allocate a range. We'll allocate 40 bytes or 40 herbs or something like that. Hardware usually can't handle big things. There's a trade-off. The modems, the wireless modems for cellular phones are really USB devices. They're USB serial devices. They're dumb little things. So we have we figured out if we have like 4 herbs in play at once, it saturates the network. It can't go in faster than that. We tried doing bigger ones, just didn't pay off.
So there are no ordering expectations where you can't get out of the application?
They're ordered in the herbs are ordered in the order in which you are submitted. So if I submit 20, they will go out in the order of that 20. They will not be out of order. Okay.
So in the error case where you submit the herb and it fails, what's going to happen there to the device? Is nothing else going to happen, or is the herb?
The herb will not be submitted. It could have failed. You could have passed invalid values into the herb. The device could have disappeared.
Right.
And so we won't. So it'll fail. The device could have disappeared between here and here.
Right.
So this submit herb will fail. So if we fail out, it will die, and we won't submit it. So we won't ever get called back.
Okay. So, but then does some device drivers say, okay, we're no longer receiving herbs, so we should, or try and fix the device, or?
Most error correction happens in user space. So we'll pass it to user space saying, hey, the write failed, or something happened bad to this device, the device went away. In user space, if you look at user space write function, the write returns how many bytes was actually written to the device. we fail that, then we need user spaces to clean up resubmit. Protocols happen there. PGP actually has protocols will handle it there. SCSI will resubmit if the error happens, and the low-level driver doesn't do that. So we handle these kind of error conditions, but most all the time it's happened above the driver itself, usually. So some things resubmit. The audio and webcam sometimes need to figure out and do it themselves.
What path do these errors take to get back to user space? Like in that case statement you had, how do those get back out?
Those don't. Those don't get back out. It could get back out in that it could be the return value from the submit error sometimes. Most of the time it isn't. Depends on the hardware. Other times it just won't get out, so you need to save that error off if you care about it. Look at the storage stuff. USB storage, we save it off, and we wake up the queue that something else happened over there. Network devices, same thing. Your network USB devices. They wake up the queue over there saying an error happened. Yeah, it gets really complex if we have 8 herbs in flight and one of them in the middle fails. What do we do? Yeah, so that's it. Go to step 6. That's it. Yeah. What? Yeah, okay, you got it working. Okay, so build this thing. Step 6. So if you go to sys, bus, USB, drivers, GoTemp, 2. Oops.
It's 100 times the temperature.
No, it isn't.
It's not?
It might have hit 4,000.
So, if you count the temperature, you see some weird number.
Yeah.
Whoa.
Isn't that fun? And here it is a perfect example. This is the raw unit from the device. We don't want to do Celsius conversion, Kelvin conversion, Fahrenheit conversions in the kernel. We will read the raw data out. We're in interrupt context. We don't know what we want to do. So here, it just happens to be some number. And by virtue of the company being nice and telling me, it is, if you multiply that value times 0.0078125, we will get Celsius, and then you convert Celsius to Fahrenheit and go from there. Here's a cool little script. Now we should read it. Now these devices also have, that's a raw value, these devices also have a calibration value in it, and we should apply the calibration value to the final version. I never got around to it, that's an example for the reader.
What did you say the multiplier was?
It's in that gettemp bash script. There's a bash script in the main directory. You just run gettemp, it'll go through sysfs to find it and watch it. And if you hold it in your hand, go up. And go to 75 degrees. So is anybody seeing zeros for here?
First time.
First time. All right, there's a bug in this driver. All right. Fun part. Let's go back. You go in the final directory. You do a little bit more things in the final directory. So there's some fun things in the init device structure function. When we first send the initialization message, the problem with this device is it wants to be acknowledged that the initialization message came back before it'll start setting the measurements. So you can do fun things like sleep for a second, or 10 seconds. After we do that, and then the interrupt will flush out and everything will be good. Or we really should do a read interrupt message here and go. It will flush it out and then we'll go to the second. And I leave that as a message, as a fix for the reader. There wasn't a read interrupt function until very recently, so that's why we didn't do it in the kernel. So you should just read it and then you can go after you submit the herb. We kick off the interrupt herb after we send off, no, we kick it off before we send off the send measurements. So if we're lucky, then we sleep another 3 seconds, and then we start measuring.
How do you know that you have to sleep another 3 seconds?
I just guessed. It happened to work. So we start reading, this will actually read the return value of the initialization, which takes a little while, and then the measurements will work. This is an example, and I left it here, of some of the fun things that you have to do in a driver, that even though the device says it works properly, that you got to work around. We do all sorts of crap in the kernel to deal with broken devices. This isn't even broken. It just is kind of odd that every once in a while we'll hit this race condition. If you unplug the device and plug it back in, it'll work. Plug it in again, it won't work. You know, we got to work around these things. This is an example of a real-world situation. I don't recommend sleeping, but you can. I mean, this is a dumb little thermometer, and it'll sleep, and you're okay. But who cares if you don't have any messages or any temperature for 4 seconds after you plug the device in? Maybe you do, maybe you don't. So that's a way to work around. We deal with this stuff all the time. And I leave it in as an example to show how this all works.
It's always guaranteed the first customer that runs it will need 2 seconds.
Oh yeah, that's fine. So then you fix it right and do it read. Another fun thing with this device, if you wave it, as you're looking at it, there's really 2 LEDs in there. I'll leave it to you to write a driver or modify this so that I give you all the commands for how to modify the LED state. All these different commands. I had one person that wrote a Python script, modified the driver, and you could drag the little diagram to see it go from red to green to red. You can do this all in user space too. This is a really dumb driver. We're just reading and writing simple values. All this should really be done in user space. It doesn't have to be done. And that's what I recommend. You can write user space drivers using USBFS and libUSB that's portable to all the other Unixes and even Windows. And that's a better way to do this. And then the best way is there's already an in-kernel driver that handles all the data acquisition devices from this manufacturer and 5 other manufacturers. It just is a simple ring buffer that reads the data from the devices and shoves it off to user space. That's how it's made. And that's an example of why Linux, with all the source code being available, works. One company wrote a data acquisition driver, finally submitted it to us, and then 3 others say, hey, that's kind of like mine, but if you modify it a little bit, so we have one driver, supports 5 different companies, a couple hundred devices, and it works for everybody. All these other companies, nobody has to maintain the driver, it works for everybody, automatically works. There's an example of us factoring out code, keeping it simple and small. There's a whole bunch of fun things you can do with these devices. There's a place where I don't know where I think it's in the non-volatile memory is where the calibration unit is. I'm not sure exactly where it is. If you can go download the software for this device off their website. It handles the user space side, and you can read it out, how to figure it out. You can graph it from lab view. So that's it. That was a lot. Does everybody know how to write USB drivers in so many fashions? Included on that tarball is a copy of the Linux device driver chapter on USB, a document on how to get involved in kernel development, how to submit patches. You have no excuse. Actually, you have even less excuses. I keep track of who does what in the kernel and what company does what. There's a talk Google finally taped it. I've been giving for a couple of years on who does what for Google. It turns out their 5th most productive developer in all of Google submitted spelling fixes. That's it. Spelling fixes. For comments, for print page, all he does. Spelling fixes. And it's great. I love it. That works. He's involved. He's helping out the kernel. But that's the 5th most productive. It's kind of sad from Google's standpoint. I made fun of him for that. But that's good. And this guy's boss didn't even realize he was doing it until they told him to talk. Which is even better. In a way, he was happy. Any questions?
Rick, you want to say a couple of words on USB 3 or whatever?
I want to say a couple words on USB 3. I'm not allowed to. USB 3 is coming. I said before we are through the Linux Foundation. I'm now a member of the USB interface group. We can get access to specs early. USB 3 is weirder in that they're locking down the specification for the contributing members only. There's 4 companies, you have to sign an NDA with them. Because it's not my vendor or not my company that's signing the USB agreement, they wouldn't let me do it individually. And if I did do it, I'd be under NDA anyway. I couldn't even talk about it. We do have USB Linux driver developers working on it. When it comes out and is in draft state, we will have support for it. I know it's going to be fast. I know there's optical connection. That's all I know. Wireless USB is there. We have wireless USB. Sorry.
Any ETA on that?
Sorry?
Any date that?
I have no idea when it's coming out. It's one of those things that they'll finally get the spec done, and then maybe a year and a half later we'll see hardware. So, okay. But, that's it. Thanks a lot. Thanks for not falling asleep.
One second, Rick. Yeah. Of course. I need a trinket.
Oh, like I mean, trips my lead.
I know. Well, and this one is specifically wrapped in blue tape, so you have to take the blue tape off.
Oh, thanks. That was my tip. Thank you.
And there's also maybe very much information. So we really do appreciate you coming.
Thank you.
very much.
Thanks for having me.
All right, thank you guys.